Computers are fascinating machines, and their ability to perform mathematical calculations at stunning speeds help us to solve complex science and engineering problems in a way that was impossible using conventional pen and paper approach. If you are curious about how these simulations are developed and want to get an intuitive understanding of its core concepts, keep watching because in today's and some upcoming sessions, I'm going to take you to the fascinating world of physics through the language of computer simulations. I'm Vaishak. Welcome to Physics, Code, and Animation. In today's session, we are going to study and simulate the motion of a ball under the influence of gravity. This is one of the basic examples that is simple enough to visualize using our intuition, but detailed enough to understand some of the key concepts in building a simulation model. Newton's law of universal gravitation states that any two objects with masses will accelerate towards their common center of mass. This is a critical assumption while considering the motion of bodies with similar masses. However, while dealing with motion of small objects on Earth's surface over very short distances, it is safe to make some assumptions to simplify the problem at hand. We will assume Earth as a stationary object, unaffected by gravity, and the ball as a single point mass. Also, gravitational attraction can be considered as constant due to the small distance covered by the ball. We can ignore the air resistance as well. With these assumptions, we can simplify the motion due to gravitational forces as a simple motion with constant acceleration. In this video, we will look at the governing equations of motion with constant acceleration, understand the concept of splitting continuous time into finite time intervals, and how to handle custom events like bouncing from the ground, how to deal with situations that can be modeled by accounting for energy losses, and so on. We will also learn how we can write these equations in the form of a computer program, use plots to visualize results, and how the program can be written in a reusable manner for future applications. So, without further delay, let's get started. We are going to follow a ball in its motion towards Earth from a height of 10 meters. At the start of our observation, the ball is held stationary at this height and then suddenly dropped. This means that the only force acting on the object is the gravitational force with Earth and the acceleration is towards the Earth's center. Before we proceed any further, it is important to establish some sign conventions. As motion can happen upwards or downwards, it is important to identify them with negative and positive magnitudes to indicate the opposite direction. We will consider every position above ground as positive and everything below ground as negative. Also, all velocities and accelerations in upward direction are considered as positive and everything downward direction as considered negative. With these assumptions, we can start building our simulation. So, as time progresses, acceleration will cause a change in the ball's velocity. By definition, we know that acceleration is the time derivative of velocity. That is, the rate of change in velocity with respect to time. This is given as negative 9.81 meter per second square. This acceleration will change the velocity of our ball by 9.81 meter per second in every second. In reality, this is a continuous process. For any infinitesimally small duration, there will be a small change in the velocity of the ball. However, in computer simulations, as we have limits on the computational speed and memory, especially in more complex problems, it is not possible to solve them for all infinitesimal instances of time. A powerful method is to split the continuously varying time into variation across finite time steps. In this session, we are going to arrive at the governing equations that can predict the velocity and position of the ball after a finite time step if we know the initial position and acceleration. This process of representing the variation of a parameter as a set of its values in a finite set of points is called discretization. In the language of calculus, derivatives represent the rate of change of variables with respect to other variables. So, velocity is the time derivative of position and acceleration is the time derivative of velocity. These are operations on continuous variables. However, for the purpose of performing a computer simulation, we can write the derivative as an approximate difference instead of taking dt as an infinitesimal time interval. Thus, the derivative dx by dt becomes x2 minus x1 divided by t2 minus t1. Similarly, for acceleration, the derivative dv by dt becomes v2 minus v1 divided by t2 minus t1. This procedure of expressing the derivatives as the difference between neighboring values has a huge advantage that they can be used to determine the derivatives numerically, even when we do not know the function but only their values at certain points. But our interest is not in predicting the derivatives of functions, but predicting what will be the position and velocity of our falling ball after each time interval t2 minus t1. For this purpose, we can rearrange these expressions for the derivatives in a convenient form. If you rearrange the expression dx by dt is equal to x2 minus x1 by t2 minus t1 by multiplying both sides by t2 minus t1 and then adding x1 on both sides, the equation becomes x2 is equal to x1 plus dx by dt into t2 minus t1, which is ideal for predicting the position of the object x2 at time t2 if x1 dx by dt are known. In the same spirit, the expression dv by dt is equal to v2 minus v1 by t2 minus t1 can be rewritten as v2 is equal to v1 plus dv by dt into t2 minus t1. Using this system of equations and the fact from our previous discussion that velocity is the time derivative of position and acceleration is the time derivative of velocity, these expressions can be simplified into v2 is equal to v1 plus g times t2 minus t1 and x2 is equal to x1 plus v dash times t2 minus t1. A catch here is that the velocity term used in the equation for position is neither v1 nor v2 but a term called v dash. This is because unlike the acceleration term in the first equation, the velocity in the equation 2 is not a constant. It varies from v1 to v2 during this interval. Our assumption is that during this interval, velocity changes linearly. If you look at the equations, it is obvious that the equation follows the equation of a line in the form y is equal to mx plus c. So we can use the average velocity during this interval for calculating the position of our ball after the interval. For a linear motion where the velocity is v1 at t1 and v2 at t2, the average velocity v2 plus v1 divided by 2 will be achieved at a time step t1 plus t2 by 2. That is exactly at the middle of the time interval. Now we have enough theoretical foundation to start simulating our ball's motion. So let's develop an algorithm for this. Our variables of interest are time t, position x, velocity v, and acceleration g. When our simulation starts, that is when time t is equal to 0, our ball is at a height of 10 meters, that is x equal to 10. The positive notation as the ball is above the ground. And velocity of the ball v is equal to 0 as the ball is at rest at the start. Defining the state of our system with all necessary variables is often called setting the initial conditions. and is a necessary step in building any simulation model. Once our initial conditions are set, we can start writing the equations to predict the values at the next time step, that is, when time t is equal to 0 plus dt. We need to find the average velocity v dash at time dt by 2 before we can find the position. A simple technique for this, without introducing any additional variables into our system, is to calculate the velocity for the first half interval first. That is, v dash can be v plus g times dt by 2. Then use that velocity to find the position after dt. That is x equal to x plus v dash times dt. Then upgrade the velocity for the full time interval v is equal to v plus g dt by 2. Notice that we are using the same variable for assignment of new position and velocity values. This reduces the number of required variables. Not much of a problem in this example, and it makes it convenient for running the algorithm in a loop. These steps can be repeated any number of times, and the equation will predict a new position and velocity of our board. So t0 will become t1, x1 and v1 will become the position and velocity respectively. It becomes x2, v2, x3, v3, x4, v4 and so on as the time progresses. But how do we know when our ball will hit the ground? Mathematically, x can take any negative or positive value. But from a physics standpoint, any x value below 0 means that our ball is below ground, which does not make much sense unless our ball made an impact crater on the surface. So let's run the simulation till the value of x becomes 0. As we are taking finite time intervals, we are not sure that we will be calculating for a time step where the ball will exactly touching the ground, but maybe slightly above or below the ground. This is a limitation in any numerical simulations involving finite time steps. So our only option is to constrain our simulation to a condition where x is less than or equal to 0 as a terminating criteria. Now we have all the tools to build our simulation for a journey of our ball from a height of 10-meter height to ground. So without any further delay, let's start building the code. For this session, I'm using Python as my programming platform. Also, with native Python, we will be using matplotlib for creating plots. Also, I'll be using Visual Studio Code for the IDE, but you can use pretty much any IDE for this. All right. As a prerequisite to developing the code, we have to import matplotlib, the library for creating plots into our code, as you can see in line 1. Matplotlib is an awesome library that has extensive options for creating a wide range of static and animated plots, and is quite simple to get started with as well. Once matplotlib is imported, our next step is to set up variables required in our simulation and define the initial condition. We have position, velocity, and acceleration as the variables to define motion. We have time to assess the progression of time, and dt is equal to 0.01 second as the time interval we chose to take between each simulation step. This choice of 0.01 second is a careful choice, as large time steps can significantly affect the accuracy and even sometimes the stability of our simulations. There are several techniques in numerical simulations to ensure stability of algorithms, and we will cover some of them in future. For now, let's focus on building a basic simulation. Next, we have two lists for storing time steps and respective positions as the time progresses. These lists will later help us to create the necessary data for plotting our results to interpret our simulation. So after all the variables are defined, now we are ready to run the core algorithm for our simulation. Remember that we said the ball will reach the ground when the position becomes less than or equal to 0. For simulating the first fall, we are terminating the simulation when the ball hits the ground. Thus, we can program our simulation to stop when the value of position becomes less than 0. This can be easily achieved using a while loop as shown in line 12. Inside the while loop, we are implementing our algorithm to update velocity, position, and time in an iterative manner. Each time, we find out the average velocity using the half-time interval technique. That is, we calculate the velocity when time is equal to t plus dt by 2. Use that velocity for updating position and later update the velocity for remaining half of the time step. We then increment the time step. This finishes the physical aspects of our one simulation step. Next two lines store the values into the list we created earlier. Once the while loop is terminated, we use matplotlib's plot and show functions to plot the position versus time graph of our simulation. Now, let's run our simulation. Alright, our simulation ran successfully and we got a reasonable graph that indicated the accelerated motion of our ball towards ground. Observing the graph, it is clear that the simulation is terminated when the position reached 0. But how much time did it take to reach there? Does it make any physical sense? And how do we validate our results before moving ahead further? Fortunately for this problem, we already have an analytical solution for the time calculation. From the equations of motion, we know that displacement s can be written as ut plus half gt square. If we substitute 0 for our initial velocity, the expression becomes s is equal to half gt square. Solving for t, we have t is equal to square root of 2 times s divided by g. Using 10 meter for our displacement s and 9.81 meter per second square for g, we will obtain time taken as 1.427 seconds. Looking at our plot again, it is quite clear that we are also predicting a very close value. That is good. The next bounces of this ball are the exact repetition of the same algorithm. And it is safe to consider that the simulation will behave the same way for all subsequent bounces. That is good. Now, one limitation of our current algorithm is that it does not have any mechanism to decide what to do when the ball hits the ground. Rather, we just stop our simulation. Now let's look back at physics to see what really happens when the ball hits the ground. If you think from your physics intuition, it feels intuitive to think that the collision will cause a momentum exchange between the ball and Earth. And in this simulation, as we are ignoring the motion of Earth, the full force exerted by Earth on the ball will cause the ball to reverse the direction with the same velocity instantaneously. If you are not sure how this is happening, I'll encourage you to work out the conservation of momentum equations, including the ball and the Earth, and substitute all Earth velocities as 0. Then you will get the same idea of velocity reversal. In an ideal world without any energy loss, the ball will reverse the direction of motion with the same velocity. Now, we know what to do when the ball hits the ground, but another consequence of this modification is that we can no longer control the termination of our simulation loop using the position. A better way to perform the simulation is to run the simulation for a fixed time interval, say 20 seconds. This can be effectively done by using a for loop instead of the previous while loop. Let's see how this is implemented in Python. The only change for the code is that the if condition for the loop and the for loop. For providing the number of iterations required, we can divide the duration by time intervals. We can run the simulation and see that the ball bounces identically for an indefinite amount of time. A natural confusion that arises from the simulation is that this is not how ball bounces in reality. Objects bounce a few times and lose their altitude and eventually come to rest. But our simulation continues indefinitely. So what's going wrong here? It is reasonable to consider that the ball is not losing any energy in this simulation so that it has the same amplitude in every bounce and it will continue its motion for eternity. But in reality, when the ball hits the ground, it will transfer some of its kinetic energy as heat and plastic deformation. During the next bounce, the ball can attain only a fraction of its initial potential energy. And this pattern will continue during every bounce, and the ball will eventually bounce for very small altitudes, and other effects which we ignored for our simulation like air resistance start to play a major role and eventually cause the ball to come to a rest. Let's add a term in our simulation to represent this effect. We can control the energy loss by introducing a term called the coefficient of restitution into our simulation. By definition, coefficient of restitution is the ratio of velocity after collision divided by that of before collision. During every bounce, instead of just reversing the velocity, now we can multiply the velocity by a factor and then reverse it. This factor can vary from 0 to 1. 0 implies complete energy loss, as if the ball fell into a mud pit without any possible hope of bouncing back. 1 means the ball will bounce back perfectly and continue for infinite time. Here, we can take a factor of to be zero point 0.9, which will give us a reasonable approximation of a bouncy ball. Now, with the changes made, let's run our simulation again and see what happens. As you can see now, the ball loses some altitude and comes lower and lower in each bounce. Our next target would be to understand how this ball will come to rest in our simulation. For that, let's increase our simulation time from 20 seconds to 1000 seconds. We can directly change the simulation time, and as we have taken the iterations to follow the simulation time, the iterations will increase accordingly. Let's run our simulation again and see what happens. Oh, something strange is happening here. The ball is taking a straight line trajectory here and is going to the negative position values. This is a physically impossible scenario and could be arising from some limitations in our algorithm. Let's zoom in and see where the problem begins. If you look around 23.2 seconds, the ball reaches roughly 2 centimeters below the ground in one iteration and reverses its velocity using our if condition and coefficient of restitution. But as we are reducing the velocity by a factor of zero point 0.9, the position in next iteration is also below 0. The if condition is checking only whether the ball is below ground level, and then it reverses the velocity again by reducing the magnitude by 10%. Thus, the algorithm gets trapped below 0 by moving in the opposite directions in every alternate iteration. The velocity becomes small, and the solution becomes unstable. There are multiple ways to solve this problem, and each of them comes with their own limitations and benefits. A simple, physically intuitive step is to fix the position to 0 whenever it goes below 0 before altering the velocity. This ensures that the position of the ball will be positive in the next iteration. Let's try and run that again. Here, I am adding the position assignment inside the if condition. So that position will become 0 before we alter the velocity. This is a fine technique if we are doing approximate simulations, but can be a problem if we need very precise measurements of time. We are abruptly changing the position by a little in each iteration, and this will eventually add up to the total time required for the number of bounces. It can be seen that this is a good enough approximation for our current application. We can revisit some of the more advanced techniques later when we calculate more complex situations. All right, so we have successfully simulated a bouncing ball for any given amount of time where the ball will lose energy eventually and come to rest. But what next? Can we simulate multiple balls with varying parameters like different accelerations due to gravity, different coefficient of restitutions, and so on? How can we use these ball models as an object in other simulations? How do we visualize the simulation in real time rather than using static plots? And how can we post-process our simulation results to get additional insights and verify some of the fundamental principles like conservation of energy, transfer between kinetic and potential energy, and so on? We will see some best practices in developing simulation models and some cool Python libraries in next segment of this video. If you have made it this far, I truly appreciate your interest in computer simulations and physics. Please let me know your comments, suggestions about the video in the comment section. Also, do subscribe to the channel to get notified on next updates. Till we meet again, goodbye.